here we can use any grids. So let's randomize it. Let's say x equal to rand. How many grid points do we want? To make it easy, let's do 8. Okay. So that we can actually look at the entries in the matrix. And x is equal to rand. So these are random numbers. Oh, I need to sort them. Sort x. Okay, so this is going to be my grid. It's basically random. Right, and my first and last grid is going to be 0 and 1. And because I satisfy the boundary condition at 0 and 1, so I don't need to include them. But I don't need to include them in the solution, but let's make it, let's include it in the grid anyway, because we need to compute some things relating to the grid. Okay, so what would the basis functions be? Head functions. And let's plot them. There is a actually cheaty way of plotting this. I of x has actually 10 values. These are my basis functions. I mean, excluding the first one and last one, which actually doesn't exist if I satisfy the zero boundary condition, right? These are my basis functions. And plotting this, the x with the identity matrix, which actually, for each row of the identity matrix, it is 1 equal to that particular point and 0 elsewhere, right? So that basically helps me visualize what the basis functions are. And these are basically head functions. Okay, now remember in finite element, what do we need? We need to pre-compute a matrix that is the inner product of the gradients of two basis functions, of each pair of basis functions, and also this. So let's first focus on this, focus on this matrix. If my basis functions are like that, how do I compute the inner product of the gradients? Okay, so first of all, let's take a look at where these are non-zero. I have a bunch of basis functions, and so if I have a basis function that is 0 is equal to 1 here, and another basis function that is 1 here, what is this? What is this? Let's say Kij. So let's denote this matrix as Kij, and this is my first basis function, right? Because this one doesn't exist, and this is my second one. This is my third one. So what is K13, for example? 0, because they have no overlap in their non-zeros. So they also have non-overlap in their non-zero gradients, right? So the only pairs of basis function that has overlapping gradients are adjacent ones. Okay. And also, if you look carefully at this matrix, the matrix is symmetric, because if I replace I and J, if I exchange them, they are exactly the same thing. All right. So there are only actually two cases we need to consider. One case is I equal to J. Other case, index. So let's first take a look at the case where I and J are one index apart. That is easy because if I is here, J is here, they only have one interval within which their gradients overlap. So that integration I have here, the integration, although it's over in the entire omega, I only need to do it within one small interval. And within that one small interval, both phi I and phi j are linear, which means the gradient of phi I and gradient of phi j are constant. Right. So I'm going to be integrating a constant function, the product of two constant functions within a small interval. That sounds pretty easy, huh? Okay, So what are these two what are these two constants? So let's say the width of that interval is h. Okay, h is going to be different for each interval. What is the gradient of the left basis function? 1 over h minus 1 over h. Exactly. What is the gradient of the right basis function? The one that goes, it's 1 over h, right? So basically the product of these two constants are 1 over h times minus 1 over h, which gives me minus 1 over h squared. What is the width of the interval? H. So the integral is going to be 1 over minus 1 over h, exactly. Okay, so we all figured it out. So h is going to be h is going to be x2 to n minus x1 to n minus 1. So that is going to be my h. So the what I call off diagonal components, which is the entry of that matrix when I and j are one index apart, which is going to be lying on the off diagonal of the matrix, is going to be minus 1 over h. All right, so I'm done. Okay, now becomes the slightly more difficult part, is what is the diagonal of this? That is when both I and j are actually the same index. I'm integrating the gradient of the basis function squared over where it is non-zero. Okay, let's look at this again. Let's take a look at the red one, the first one. The gradient is going to be non-zero at two adjacent intervals, right? Right? So over these two adjacent intervals, I need to integrate the gradient. And the gradient in this case is, again, either plus or minus 1 over h. And after I square it, it's 1 over h squared. After I multiply it with the width of the interval, it's 1 over h. Okay, so the diagonals are the summations of 1 over h among of two adjacent intervals. So it's 1 over h, 1 over h, 1 to n minus 1, plus 1 over h, 2 to n. These are my diagonals. And the remaining task is to put them into the matrix. Okay, so let me see how many diagonals I have. Length diags. So I have 8 diagonals. That's exactly the number of basis functions I have. I have 9 of diagonals, which I'm not supposed to. I should only have how many of diagonals? I'm supposed to only have 7 diagonals. So which of them are not necessary? First and last, exactly, because I'm multiplying the gradient of 2 functions, but using here the basic functions corresponding to the non-existing nodes, right? The 0 node and 1 node, which are not part of the basis function. So I will set off diax equal to off diax 2 to n minus 1. All right, so here I'm all set. Now I'm going to construct my matrix. K is going to be diag of diax. Okay, so let me open this K. Okay, now I get 0. Oh, here I need to dot divide. Oh, I see. Okay, that means my off diax is also wrong. Is that right? Okay, so let me see K equal to this. Oh, okay, now I get a bunch of non-zero K's, and some of them are big, some of them are small. Let's take a look at why. The first one is big because I have a huge gradient over here. This is small because on both sides they are kind of shallow, and this one is big again. And this one should be bigger. 4 is even bigger. That's right. Okay, I'm happy. All right. So these are the diagonals. And I need to k equal to k plus the off diagonals. Oh yeah, I need to cut my off diagonals. Yes, thank you. All right. K equal to k plus diag off diags. I need to shift it by 1. So I'm filling this part. I also shift by -1 to fill this part. Okay, so I get a good pi-diagonal and symmetric matrix. That is gonna be my matrix K. All right. Any questions? Okay, I also need a matrix B. Need a matrix B, Bj. And this matrix K is usually called the stiffness matrix in finite element. It's just because for structural dynamics problems in which finite element is originally most popular with, this K actually represents like the stiffness of the solid body or something like that. So this is usually called stiffness matrix. And the B, let's compute B. B is the input product of F with Phi J. So let's just to do the simplest demo possible today, let's take F equal to 1 everywhere. So we just get an integration of Phi J within the whole domain. Again, let's look at all these Phi J's. If we integrate one of these over the whole domain, what would it be? We're integrating a triangle, right? And the area below this triangle is the base of the triangle times half of the height, which is basically 0.2 times like the sum of 0.5 times the sum of adjacent intervals. So my B is going to be 0.5 times 0.5 is the height of half of the height of the triangle times h1 to n minus 1 plus h2 to the n. All right. So that's my B. And next, I hope everybody can tell me what to do. U is equal to K backslash B. Okay. Now I get my U. Oh, minus. Thank you. Minus. Okay. Now what's next? Next is I want to plot. Okay, so U only has the interior nodes. So let me plot my X with 0, U, 0. So that adds like the boundaries onto my solution, right? Let me close. Okay, that's my solution of the finite element problem, where the solution is supposed to be a quadratic, right? And let's take a look at how good the solution is. And let's plot them in these circles. Well, the mesh is very coarse, but let's actually plot the analytical solution. X-axis is equal to length space 0 to 1. Let's do 1,000 points. The analytical solution, what is it? So the second derivative is equal to 0. Is equal to 1. That means the analytical solution is going to be minus xx times x minus 1 minus xx. Is that right? Should I divide by 2? I need to divide by 2, right? Right? Am I doing that correctly? Okay. I'm gonna hold on. Huh? I have something wrong here? No. Okay. Plot xx uu. I'll see in a second. Okay. Looks like